buenos dias a todos. É grande prazer estar aqui com vosotros. Now in English. So what I thought that was more logical to bring here today is not a precise research line, but to share with you what we are doing in the Lisbon Planetary Systems group at this time. So let's start. So these bodies with a square are the only ones that have atmosphere in hydrostatic equilibrium. And there are a lot of numbers, but I want just to focus your attention in the relative composition. The thing is that first, this talk is twofold. First, I want to share with you our goals, so the answers that we want to contribute to regarding research. The other one is the research lines that at this time we are developing in the Lisbon group. So the thing that I want to pinpoint your attention is, well, these planets are so different. Usually we say that Venus and Mars are very much different from Earth. Is this true? I don't think so. It's the opposite. So if we look to the composition of the two atmospheres, besides all the differences, of course, between Mars and Venus, they are more or less the same. Do we expect this? Of course. If they were built more or less in the same region and from the same building blocks from the protoplanetary nebula, I was expecting that these bodies, at least in the principle of their story, they had more or less the same composition, as we still see here, the fingerprint between them. So the different one is this, is Earth. How come? Well, everyone knows this. I will start with an explosion. You know something about the formation of the moon between Theia and the state of the art, the explanation of this, that we know. But there are some science is related with perhaps the impactor was the water waves that brought a lot of water. And remember that the isotopic ratio of the water on Earth, well, it doesn't move very well with the water in asteroids. And there are isotopic ratios studies, for instance, in this major study that makes sense if this body comes from, it was a water world. So this is one of the studies that we are developing now with celestial mechanics and the odds related with this model of the evolution of the and formation of the solar system to see if it was possible due to a early formation of Jupiter that brought this hypothesis, and well, the apport of this immense amount of water to Earth made a lot of difference. And once related with the difference of volcanism, for instance, between Venus and Earth, here we have plate tectonics, and our evil twin, there is no plate tectonic, at least today. And how come? Why? Well, we have a lubricant in these crust layers, that is water, that enhances and allows that they move apart. And with the water in the oceans that works as a sponge to dissolve the CO2, so that, yes, makes the difference between what is today the atmosphere of Venus and Earth. At least it makes sense. And of course, there is a lot of study that we must do. But this is, I would say, a major goal that we want to contribute, the temporal evolutions of the planets and compare planetology. Another thing that is important is related to magnetic field. Yes, we know that there is no internal magnetic field on Venus, of course. It's a slow rotator, so the dynamo effect doesn't work very much. So, of course, that we know that there is a induced magnetic field in the higher layers. That's true, but and Mars. But Mars, the day is 24 hours as on Earth. So what is the difference there? Well, imagine a huge bread. I used to say in Portugal, a pão alentejano, that is a big bread, and a bread roll. And thermic conductivity explains that the bread roll, it cools down much faster than the pão alentejano. So that makes sense related to why we don't have today, we had in the past, as geology shows us on the rocks, but no today magnetic field on Mars. So this is to understand why there is this evolution on the planets, because usually we study a candid camera shot of a planet. When we are studying, we see today, but it's very important to understand how they evolve with time. And so now we can understand why Mars and Venus are so different. Well, now let's go to what we do. And one of the things that we do is Doppler velocimetry based on the backscattered solar radiation in particles in suspension in the atmosphere. On Venus, that works well with the cloud layer that covers completely the planet. And so is what we do. I will not go in details, but if you have questions, I will be happy to answer. So we retrieve, in fact, using all the shifts in all the lines, what we do is to retrieve the motion of the particles, so the winds in the atmospheres, or perhaps also waves on the atmosphere. And we can use different spectrographs, high resolution ones. We must use high resolution ones, and could be fiber fed as espadons or ARPs or slit spectrographs. And we used to do coordinated observations with spacecraft and with direct collaboration with Xavier Peralta, also known by Xavier Pereira. And we did this kind of coordinated observations using cloud tracking and Doppler velocimetry. So, and it's what we do very often with the coordinated observations I was saying. So let's go directly to now the results I will show you after. First, I want to talk about the elusive molecule, at least for us, called phosphine, that was claimed to be in the higher layers of the atmosphere of Venus. Well, we, with Teresa Ancana and Clara Souza Silva, we tried to support this claim of detection, but in other parts of the spectra, important part of the spectra of the phosphine in the infrared, and so we didn't find anything. So it was totally flat. So for us, it was in fact a no-go. So, but I can't claim too much because we earned 3 space missions to Venus. So it's better to be quiet about this. So no, in fact, phosphine, but we had Envision and Veritas and Da Vinci, hopefully. So this is the first claim here by Sarah Greaves, and the first paper from Ancranage and from our observations. And here, what I want to show you are our Doppler velocimetry. No, this is the cloud tracking from the night side that we were doing from the ground. So we can do it from the ground using spice kernels. So like the telescope is a spacecraft, and it works. It works. I think that Picard Elizabeth is in the room could see that it matches very well with his wonderful results. Okay, so again, our results with Doppler velocimetry and cloud tracking, what we could see is that we were not sensing the same level of the altitude level at the same time. In fact, there was a gap of about 2 to 4 kilometers, as you can see here on the left from the cloud tracking, and on the right with the Doppler velocimetry. What we can see at modeling is very important for observations. So they helped us a lot in preparing the observations and to anticipate what altitudes we could be sensing. So this binomial between modeling and observations is really very effective. So these are results from the meridional wind using the Doppler velocimetry, and it's from different runs. And as you can see, it's quite stable. And I would say that this technique provides a very good approach to measure the latitudinal profile, of the meridional wind on Venus. So again, so with that, if we are measuring at the same time, we can measure the vertical shear of the wind. That is very important to understand a little bit better the atmosphere of Venus. So this Akatsuki, of course, is still running, and is a lot of collaboration with them that we don't know is about ENVISION. And about ENVISION, what I want to share with you is, of course, its surface, as we already heard today, and the lower beneath the crust, and the transition of it from the lower layers on the crust to the surface, and also the lower layers of the atmosphere, but also look for and research about volcanism. And so we were thinking about, there are two main things to, and I will be fast just to pinpoint that the volcanism is a major goal for ENVISION. And we started now to model plumes, volcanic plumes, and also study the SO2 variability and the hotspots on Venus using all the data from Venus Express, from ESA, and also from Akatsuki, and what we are doing at this time. So we already performed this. So this is a paper that is in preparation, final stage of preparation, about volcanic plumes. What volcanic plume? Of course, that we must compare with the ones we know on Earth. This is modeling, of course, but this is a first step. We are finalizing this paper, as I said, and about atmospheric waves that Xavier already showed us. We studied and characterized atmospheric waves on Venus, but also now on Mars. So there are waves in several planets on the solar system, and we have a paper that is submitted to Astronomical Astrophysics for Mars, and we have one paper from last year on Venus. And the thing is that we are going to look for the minor compounds in the atmosphere that could be connected with astrobiology. I thought I told you about phosphine before, but here is about methane on Mars, and we want to try to contribute to disentangle if this methane comes from the serpentinization of olivine, perhaps, or if there is another interesting reason for that. So I already said that modeling is quite important and helped us a lot in preparing the observations. And sorry, showed it. So on Mars, what the thing is, are interested is, why is so dry today? What happened to the water? We know the marks on the water, everyone knows. And what we are studying now is the ancient shorelines of the northern hemisphere ocean. And the fluvio-marine regions, we are studying them, the DTMs, and also now we're studying the reflectance, and to study the minerals that could have a fingerprint of perhaps previous life on Mars. We don't know, but we are looking for. So another thing that we are doing now that is done, we will submit the paper. I'm a bit lazy, but might be already submitted about when we have a global dust storm on Mars, we have a medium in suspension in all on the planet. So we take advantage of this to study the backscattered solar radiation with our Doppler velocimetry technique that we also applied. So we apply for Mars. So we already have the paper done. And so this is what we were doing from the ground. But this technique is, again, the same thing, well, what we did. So I will not go in details. But the thing is that this is related with the isotopic ratio that we are studying and is very, very, very important. So almost in the end, it's just to share with you the different work lines that we have now. This is with also on Mars. So finalizing with Titan, where we are doing the same thing. It seems that we found, let's see, I'm optimistic, sometimes too much, that we found C3. And this is a very important molecule, as some of you know very well, related to astrobiology, that is the missing link. It seems that we found it. Don't lose the next episodes about that. So we are preparing the paper now and will be submitted in a couple of weeks if everything goes smooth. And for these are the lines we found related with C3. We also have results about methane, but I will not tell you about this. And to finalize about the exoplanets and the synergy about what we already know from the solar system and the synergy with the exoplanets characterization, that is a new adventure. So we are connected with Ariel, the space mission, where I am co-PI of the mission. These are a lot of systems that were already found. There are thousands, zillions of planets. And so we'll have to work for a long time. So here on Ariel, we are exploring the relations to what we know in the solar system. So last thing, during the last transit of Venus, there was transmission spectroscopy here in this aureole. So this we are learning on the solar system, and this is a unique data that will calibrate transmission spectroscopy for the exoplanet. So this is a very important result. This I will skip. Next time that I will visit you, I will tell you about this. Thank you so much. So we must disentangle between